Okay, so as I said, today I'm going to talk about a equilibrium concepts that are slightly different than Nash equilibrium, and have motivated by evolution and ideas from evolution. The reason I'm going to speak about this is that there's growing interest in game theory from a machine learning point of view. One is about adversarial learning and things like that, and also genetic algorithms as a way to search in spaces where there's many parameters. So that's one of the motivation to speak about this, and specifically the notion of stability that has to do with evolution is interesting also because whereas this classical Nash equilibrium is more declarative in nature, this notion introduces some dynamic that you could think about. So from that perspective, it's also interesting. So let's consider the following simple game. So you have two actions. There's two players. Each one of them can act as small or as large, and these are the payoff. So can anyone tell me what's the Nash equilibrium here in this game? So maybe I'll remind us what a Nash equilibrium is. So if this is the payment and X and Y are actions, so a Nash equilibrium is such that if player number 2 changes its action to Y prime, then it loses. Or if player number 1 changes its action to some X prime, it loses. Okay? So that's the definition of a Nash equilibrium. Now, if we go back to this game and consider playing, both players play small, okay? So they get 6-6. If player number 2 changes its action to large, then it gets 10. So it's so 6-6 is not a Nash equilibrium because player number 2 can deviate to L and it will gain from 6 to 10. It will gain 4. Okay? So the conditions of a Nash equilibrium for 6-6 is not met. So small is not a Nash equilibrium. Can you see what a Nash equilibrium is here in this game?
Are you sure there is one?
Yes?
Both are large.
Yeah, if both players play large, then they get 4-4. Now, if player number 1 changes, it goes to small, and player number 1 will get 1 and will lose. If player number 2 goes from large to small, it goes to player number 2 gets 1 and loses again. So 4-4 is a Nash equilibrium here, okay? Very good. By the way, do you know what the name of this game is? This is the very famous prisoner dilemma game, okay?
Yeah.
Anyway, the interesting point is now that we're going to look at this game from a totally different perspective. So instead of thinking about a player that can play S and L, we'll think about two species. Okay, there's, if you like, some type of animal that is small, and then some type of animal that is large. And they compete on food, maybe. Okay, so if two large players are competing, that's why they're getting less. Okay, if a small and a large animal is competing, then maybe the large animal is stronger, then it gets most of the food. So that's a totally different perspective of this situation. So we're thinking now about two animals, basically, small and large. And then we're thinking about a population of these types of animals. So maybe I have only small animals or only large animals. And a mutation might introduce into the population a small percentage of the other type. So maybe I'm starting with small animals, and then a small percentage of large animals are introduced into the population. And the question we're going to ask ourselves is, what happens when these other type of animals are introduced into the population? We'll introduce the concept of invading. So we'll say that, say the large animals invade the small animals at level X if we introduce X percentage of large animals into the population. Same, the other way around, S invades L. So basically we introduce X percentage of S into the population. Now the question, the stability question we're going to ask ourselves is whether an invasion will cause the average gain or in evolution from the theory of evolution point of view, we would refer to that as the fitness of the animal. So the average gain of a certain animal, how is it impacted by the invasion? Okay, so think about it as say we have a situation where L of the large type invaded, then basically we're looking at a meeting of large and large in certain probability, or large and small in certain probability, or small and large in certain probability, because of these percentages. And when they meet, the outcome is determined by this same matrix that we talked about previously. So let's see what S is going to be doing if X is invaded by L. So with probability X, we're going to have the situation SL, and S is going to get 1. With probability 1 minus X, we're going to get the situation SS, so L is going to get 6. Overall, L is going to get 6 minus 5X. Okay. Is that clear?
Yes.
Okay. Now, what is L going to be doing? So with probability 1 minus x, L is going to meet a small. So we're going to have SL, and L is going to get a 10. And with probability x, L is going to meet an L, and it's going to get a 4. So overall, it's going to get 10 minus 6x. Okay? Now, 10 minus 6x is this line, which is consistently bigger than this line. Okay? So overall, we're going to say that S cannot block the invasion of L. So conceptually, L will grow bigger, and L will be more fit, and as a result, the percentage of L is going to grow and grow and grow indefinitely until it becomes totally an L world. Okay? As an exercise, you can try to see what happens if S invades L. You would see a similar result. So the end result here is that eventually the world is going to be 4-4. Okay? So the evolutionary stable strategy here is LL, because S cannot invade L. And if L invades S, it just succeeds. So one interesting thing about this, so you see the dynamic, right? The evolutionary stable notion is dynamic, and it has to do with this invasion of one gene over another gene, or one type of animal over another type of animal, or in some application of game theory, one type of film over another type of film. So that's one interesting point. The other interesting point is that we've converged to the Nash equilibrium. So basically, there's an agreement here. It's not if and only if, but we see that we got the same thing here. The relation between the two is interesting, the exact relation, but you see there's a relation in the example at least. But maybe the most interesting thing from an evolution theory point of view is that the species that emerge as the only species, the large, ended up with a fitness of 4, which is smaller than 6. So that kind of seems to be in contradiction to evolution ideas, because the fitness of the species grows. And here we converge to, say we started with S and L was introduced, so we converge to a lower fitness. Okay, so that's food for thought. How is that possible, that we converge to a lower fitness? Is it a contradiction to evolution theory or not? Okay, any questions or thoughts about this? Please unmute when you speak. Was it clear to you?
Yes. Yes.
Okay, good. So thank you very much for joining, and we'll speak next time.
Thanks,
Thanks.
Eitan.
Bye.
Thanks.
Bye bye.
איתן, אתה רוצה שנתחיל עכשיו או ב-3:30? איתן?